This is a digital multimeter. It is a double-edged instrument. It can enlighten you with knowledge, but it can also trick you with false information. It can save you money, but it can also cost you money. It can increase your safety, but in the wrong hands and used incorrectly, this meter could also endanger your life. A carpenter has a hammer, but a electronics technician or someone who wants to learn more about electricity and electronics has a multimeter. This is by far one of the most heavily used and basic devices all over the world in all sorts of applications and all sorts of professions 24 hours around the clock. Even if you're not an electrician or a jet plane mechanic, learning to use this device can really be beneficial to you over the long term. Even if you only spend a few minutes learning a few basic functions on the meter, it will really pay you back in the long term and give you the opportunity to gain more knowledge and more understanding. This presentation will do three things simultaneously. It will provide beginner level knowledge and introductory information. It will also provide intermediate to advanced knowledge. And finally, it will include safety related topics. Okay, let's get started with the video. One of the most basic and common jobs that you will need a multimeter for is to take a voltage measurement. This is the dial of a typical rotary switch multimeter. At the top of the dial on this particular model, there are two locations for voltage settings. The first is right here. This is your DC voltage. And on the right is your AC voltage. The way you recognize the two is usually AC voltage will be represented by what looks like a tilde or a squiggly line. That just represents the AC sine wave. Over here we have a V with three dots and a line above it. Anytime you see that, that usually means DC voltage or direct current. Now, it's important to understand that DC and AC are two completely different worlds. They are not the same, they don't behave the same, they don't work the same. If you're going to be using a digital multimeter to measure any kind of voltage, you should at the very least research and study the differences between DC and AC. This is just for general understanding, but also for safety reasons. To keep this short as possible and encourage independent research, I'm going to very briefly explain the difference between DC and AC. DC, or direct current, is a continuous flow of electricity with a positive and negative polarity. AC, on the other hand, is alternating current. It usually goes back and forth between positive and negative rapidly 50 or 60 times a second. In North America, it's 60 times per second, or 60 cycles per second, also known as 60 hertz. And in Europe or other countries, it may be 50 hertz or something else. Some cheaper multimeters may not measure AC very well. If you're measuring the output of, say, a modified square wave inverter, it may give you an incorrect reading because the meter is not able to deal with the output that it's getting. So if you've ever taken a cheap multimeter and stuck it into the AC outputs of a modified square wave inverter or something similar, and were alarmed to find that it didn't read what you thought it should, don't worry. It's probably just the meter being unable to read the output. Next thing to understand is that a typical rotary dial multimeter like this will have different scales of voltages that you can select. They're also called ranges. If you are not sure what you're measuring, it's a good idea to start with the highest scale first. Let's go ahead and start with a DC voltage measurement. So we're going to go with DC, which is right here on the left. Let's go ahead and switch it to 500 volts DC, which is the highest level that this meter supposedly can measure. Warning. You should never ever try to measure high voltage DC with a entry-level multimeter and low-cost, low-quality multimeter probes attached. It could literally end your existence. But in this case, for the example, I'm showing you a normal procedure that is generally taught that if you're not sure how high the voltage is, you should start with the highest range of voltage that's available on the dial. So that's what we will do. The meter will first usually jump the numbers around a little bit. This is very common. It's just the meter's way of calibrating itself. It's also called reaching zero or zeroing out. So as you can see, the meter has zeroed out. And the reason you're seeing the polarity sign flash regularly, that's right here, this indicates positive or negative, is because the meter is quite sensitive and it's trying to constantly measure the voltage. And believe it or not, even when the probes are not connected to anything and are just laying on the ground, here's the probes right here, they actually can generate a voltage. And if you put the meter on a more sensitive scale, it's possible to even get that number to change. So you'd be putting a tiny bit of voltage into these probes from just your fingers or whatever stray voltage you're picking up. Now that we're on 500 volts DC, let's measure a voltage source. So I'm just going to use this lithium iron phosphate battery here as my voltage source. Now the first thing to notice about a multimeter is it is got a positive and a negative connection. And you always want to make sure that you're plugged into the positive and negative on the meter, because this meter actually lets you choose which one you want to pick. Now if you can see here, I've made a common mistake. This probe here was plugged into the 10 amp range. If you look, you can see that the common port there had nothing in it. This is going to be a safety warning and a cautionary tale about what not to do with a digital multimeter. Before you start measuring anything or using the meter, always look to see where the probes are plugged into. Now to make this easier, I'm going to take the probes out and I'm going to show you the connections on the multimeter. We have 3 connections here. It is important to note that the connection between common or ground and the 10 amp terminal on the meter is literally a direct short. You never ever want to plug your probes into those 2 sockets and connect them to a voltage source. This configuration is meant to be placed in series with a load, not across the terminals of a battery, which again would be a direct short. Please note that there are exceptions to this rule. For example, connecting a small solar panel directly to the 10 amp socket in a direct short through the meter is a quick and easy way to measure the short circuit current that solar panel would be able to deliver. As long as that solar panel does not exceed 5 or 6 amps of current, it should not damage the meter in the few seconds that you have it connected. But if you were to try to short, say, a battery through this terminal, it is able to deliver far more current and would quickly burn out the meter in most cases. It would probably also damage your multimeter test probes and/or test leads, so that's something to keep in mind. To take a voltage measurement, only the bottom 2 terminals will be used. The top one, or the third one at the top, will never be used for anything except measuring current in series. Now this is very, very common. I don't say that all multimeters are like this. Some of the newer models may not have this, but by and large, if you pick up a basic digital multimeter, it's going to have these 3 connections. And what's printed here on the face may vary. It's common to have different layouts and different icons, but this is very basic information. It's fairly universal. So first you have a common, and there'll be some safety warnings here. And what these are telling you is basically, look, this is the maximum voltage this meter is able to measure. This is the maximum voltage you should ever put through it. Here is the maximum amount of current or amps that you should ever put through the meter. I would never put through 10 amps, but it says it can handle 10 amps for 15 seconds maximum every 30 minutes. It's up to you whether you believe that or not. I would never put 10 amps through this meter. Next, we have some information here about what this terminal here can do. So this is referring to this middle terminal right here. And this terminal here is for volts, ohms, and milliamps. It can measure 500 volts DC, 500 volts AC, or 200 millivolts, or milliamps, sorry, max. And here we have common, COM, and we have ground. This symbol here is a universal ground signal. It means common or ground or both. And that's 500 volts max. So common means that pretty much you'll always be plugged into here. And this is also known as negative. Ground, negative, common are 3 things that are pretty much the same thing up to a point. Generally speaking, they are tied together. So I'm going to plug my negative probe, or the black one, into common, ground, or negative, whatever you want to call it, this hole here. This connection here is for positive. Even though it doesn't really say that, it's just understood that this is positive. So folks, if you're going to use a multimeter, you always want to start, even before turning it on, look and see where it's plugged in. Do that before you do anything else, because worst case scenario, you could destroy your meter, and you don't want to do that. And I'll explain why later. So first, I'm going to take my negative connection. And by the way, these probes did not come with the meter. These are better quality probes. The ones that come with cheaper meters are usually not very good and they fall apart. For $10 or $12, you can get a new set of probes about like that. These are around $10 or $12. I don't remember exactly. And they're a great improvement. And I do recommend, if you're going to use a meter seriously, go ahead and get some better quality probes. You don't have to spend a bundle on the meter, but get some decent probes just for safety and long-term durability. So I've attached my negative probe to common, or ground. Next I'm going to take my positive, and I'm going to plug it not here where it was. Originally, my 2 probes were plugged into these 2 connections here. So I'm going to plug my probe into volts, ohms, and milliamps, which is right here, which is also positive. And that will enable me to take a voltage measurement. Okay, now that we have the probes properly inserted into the meter, and not into the 10 amps connection right here, as they were when I first picked the meter up, we can go ahead and measure this battery. So here's the battery I'm going to use. It doesn't matter. It's just any old battery for an example. Now let's take a look and Let's measure using the correct polarity. So I'm going to use positive and negative correctly. As you can see, the battery has a red and a blue or a black for negative. So I'm just going to take the probes, and I'm assuming here that we're measuring a simple car battery. It's not high voltage, and it's relatively safe. And so this is a great way to begin learning how to use a multimeter. Just measure small batteries and things like that until you're comfortable. Okay, so next I'm going to take the probes, and I'm just going to place them on the terminals of the battery. And what we have is 13. So I know this battery puts out direct current or DC. I know I'm on the correct range. It's voltage in DC. And I know 13 volts is kind of close to what this battery ought to be. I know at rest it would be around 13 volts and some change. If you'll notice here, there is no decimal point. It just says 013, which is not very useful. When measuring a small battery, you really want to know what is the actual voltage. So that's where the scales or ranges come in. 500 volts DC is not going to be able to show me much information after the decimal place. In fact, on this range, it doesn't have a decimal. But if I switch it to 200, which is a smaller range, you see the decimal point appears. You can see the decimal point right there. If I put it back on 500, it disappears. So it's just showing me a whole number. But if I switch it to 200, now we have a single digit after the decimal place. Now, more expensive meters might do better than this. This is a fairly basic meter, but that is the point of this video, is basic equipment, basic entry-level knowledge. Now I know my battery is nowhere near 200 volts. It's just a little 12-volt battery. So what I'm going to do is I'm going to go ahead and step down to 20. And now you see the decimal place jumped over again. Now if you look, it's jumping back and forth. No decimal place. There's a decimal place. And again. So 20 is very, very common on meters like this. 20 volts covers a lot of different things. It can cover a car battery or just anything. A 5-volt power supply. Lots of things fall under 20 volts. And by the way, 20 volts is never going to electrocute you. It's safe. If you touch it with your hand, you'll be good. Generally speaking, 48 volts is considered to be the edge of safety. But 20 volts, you're fine. You're not going to get electrocuted by 20 volts DC. Now you'll notice something else. This is important to keep in mind. The lower you go on this scale, so right here I've jumped down to 20, the lower you go on this scale, so going this direction, the more sensitive the meter becomes. And it's probably not a good idea to connect the multimeter probes to a potentially high voltage source when the meter is in a lower scale. I'm not saying it will damage it, but it could. So in this case, I know my battery's low voltage. 20 volts is fine. I'm going to go ahead and make the measurement. Now here's something else interesting. The more sensitive the meter becomes, the easier it is to get stray voltage readings. Now watch what happens when I touch the probes. You can see the meter is reacting. It can even pick up a little bit of electricity from my fingers. So this could be a problem. Right now it's not a problem, but it's just something to be aware of and keep in mind. So with that said, let's go ahead and measure the battery. The probe's on the battery. Now that's a lot better, 13.15 volts. This is a lot easier because on a low voltage system, even a tenth of a volt matters. So this decimal place here is a tenth of a volt, and this is a hundredth of a volt, or 0.15. Or you could say 15% of 1 volt. Depends on how you look at it. So the voltage is 13.15 volts. The next thing to be concerned about is that negative sign that keeps flashing on the left side of the screen. That's simply telling you polarity. Now, because the meter is very sensitive and it's picking up stray voltage, it keeps flashing the negative sign because it's just picking up random noise from the environment that I'm in. That's nothing to be concerned about. If anything, it tells you the meter is awake and it is trying to take a measurement. What happens if I take the positive probe and put it on the negative terminal of the battery? Let's try that and see what happens. And this is one of the most useful functions of a multimeter. It says negative 13.15 volts. Now, as you can see, I've got the red probe positive on the negative of the battery, and I've got the negative probe on the positive side. So, of course, it's now telling me the polarity is backwards. This is by far one of the most useful functions of a multimeter. It's called a polarity check. If you're not sure which is positive and which is negative, this meter could save you $1,000 simply by telling you, hey, don't hook that up backwards. Now, that's universal information. It applies to solar. It applies to household electronics, any kind of appliance. Just a universal piece of knowledge that everybody should be able to know which is positive and which is negative. However, it's worth keeping in mind that if you accidentally swap the positive and negative connections on the meter itself, that test is useless because it's going to trick you. Now, in the interest of keeping this video fairly straightforward and not getting too long, I'm not going to demonstrate these last two ranges on the scale. So 2000 M and 200 M is referring to millivolts. These are 1,000th of a volt. Generally speaking, the average person would not care about 1/1000th of a volt. But this can be very useful, and it's a very sensitive range on this meter. You would need to be careful what you plug this into when it's in the millivolt scale. And 200 millivolts, very, very tiny amount of voltage, probably not useful in most cases. However, when you do need it, this is fantastic. You can measure voltage drop and all sorts of things. I will briefly say that an interesting use of a low scale like this would be to measure the voltage drop across a long wire run, or possibly a shunt that's measuring current in a live circuit. However, this is a rather advanced topic and won't be covered here. For solar and general household use, the 20 volt DC range is probably going to be the most commonly used for a very wide variety of chores. Next, let's move on to AC voltage. So if you recall earlier, this is the AC portion of the scale, and it's in 500 and 200 volts AC. In North America, we generally have 120 volts AC, more or less, coming out of the wall outlets, but in a dryer plug or in a hot water heater, you would have 240. So these two scales are going to be the most commonly used in North America. So I'm going to go ahead and switch over to 500 volts AC. I'm going to let the meter zero out. It's a good idea to give the meter 5 or 6 seconds to zero out and reach a zero, which is what this meter has done. If it's jumping around a lot or doesn't say zero, then there could be something wrong with the meter. You may have a bad battery, or you may need to just wait a while for it to settle down. I'm going to do something on camera that is probably ill-advised for most beginners. Nevertheless, I'm going to show you how it's done. Here's a pretty typical AC power cord on the left here. It is live, it is plugged into the wall. There is going to be a time where you might want to measure a cord like this to see is there any voltage coming out at all. So I'm going to show you how I do it, and this is generally dangerous if you don't know what you're doing. Now before I take this voltage measurement, can you think of something that you should always check on the meter before doing this? Well, there's a number of things, but the first is, yet again, make sure you aren't plugged into this socket right here. Again, this connection here and this connection here is a direct short through the meter. So if I were to have both of my leads plugged into this socket, and I try to measure the voltage here, there's not going to be any voltage measurement taking place. What's going to happen is a short circuit straight from the wall outlet through the meter and then back in. And so it will burn up your meter, and it could actually electrocute you or start a fire. But you can see I'm not plugged into this socket for 10 amps. I'm plugged into common and volts, ohms, and milliamps right here. So I'm using the meter correctly. The next thing is I never use both hands when measuring a high voltage. What you don't want to have is you want to have voltage flow up one arm and out the other and through your heart. Now this is basic universal safety information. It could get really, really complicated. I could say wear gloves, wear a full body suit, ground yourself, or something like that. But I'm just going to give you the basic information. You should do research on your own before attempting anything like this. What I like to do is hold the probes kind of like chopsticks with one hand and use that to take the voltage measurement. That way, if I made a mistake or the voltage was very high, at least it's only one hand in the circuit, and I don't potentially have voltage coming through one hand and going up the arm and then going out the other hand. That would go right through your heart. That's not to say you're safe, but this is certainly something that you can practice just to give yourself some discipline and increase your safety. So with that, let's take the voltage measurement. Now this is to simulate the wall outlet in a house. In this case, I have to hold the extension cord to get the footage. Not sure I recommend that, but I'm going to do it. First thing I'm going to do is take the probe and I'm going to shove it into one side of the circuit. Then I'm going to take the other probe and put that in. And now for a quick safety warning. Here I'm taking the measurement from the extension cord, which is a substitute for a wall outlet in a house. And you can see I've got the probes going in there, and those probes are live. So the piece of metal you see sticking out there, if I were to touch that, I would be instantly electrocuted. So you can see why this is not really recommended for beginners right at the very start. You really shouldn't be doing this until you've gotten some practice and some experience, and hopefully have someone around who is maybe an electrician and is more experienced with these matters. But I'm showing you this on camera because I want people to see how easy it is to make a mistake and get electrocuted. It's important to keep your fingers away from the ends of the probes, and that's why they have these finger guards right here. You should never have your finger past this guard. You should never have your finger down here. Like you can see right here how easy it would be to slip and touch a live wire. Okay, so I'm taking a measurement of 116 volts AC, and that's about right. It could be 110, it could be 120, it could be somewhere in between. I'm not too concerned about it. That's about what I expect to be coming out of a live AC cord plugged into the wall of my house. Now, what if I want to measure it from the 200 volt range? What would I do first? Resist the temptation to just reach up and turn the dial. Because if you do that, this dial is connected to a bunch of copper contacts on a circuit board, and you potentially could be switching a heavy load through these contacts. These contacts are not meant to switch any kind of load or voltage. They're meant to make a setting change and then take a measurement in that order. If you take a measurement and then switch this dial while you're taking the measurement, while current is flowing through these leads and into the meter, you could damage the meter. Also, this may not happen immediately. It could happen over time. You don't want to start having sparks inside the meter, which would over time damage this rotary dial. So that's something good to keep in mind. And it's also not particularly safe. You could have arcing or something like that, and we don't want that either. So what I'm going to do is I'm going to disconnect the circuit. I've taken my meter probes out, and now I'm going to switch to the 200 volt range. You can see that we now have a single decimal point, which for AC is kind of overkill, but in this case we're measuring the household power, so we really don't need a decimal point. But as you can see, 117.1 volts. So once again, that's a good reading. That's more or less what I would expect. And a really interesting use of a meter like this is you can plug your meter into a circuit and then turn on an appliance and see how much voltage drop you get on that same cord. If it drops to almost nothing or under 100 volts, you know there's something wrong. It could be a bad extension cord, a bad appliance, and it could mean that there is a bad connection somewhere. In this case, the cord has no load on it, and so I'm not going to see a voltage drop. There is some variation, and that variation is happening on the meter because this is a live household with appliances being turned on and off. Things are changing, things are powering on and off, and so there is going to be some variation in the line voltage, and having a single decimal place is enough to see even small changes. It's very interesting to watch. If I turn on an appliance, you'll actually see that change. So let's do a quick demonstration here. If you look in the background, I still have my probes plugged into the extension cord, and this is on a single 20 amp circuit in my house. So I'm going to go and turn on an electric heater on low, and you'll see that voltage drop. Let's go ahead and do that. I'm going to walk across the room and leave this here, and I'm going to turn on the appliance and watch what happens. Okay, I've turned on a basic electric heater to around 600 watts. And as you can observe here in the example, hopefully you can still hear me over the sound of the heater, the voltage dropped to 107.3 volts. Now, why is that voltage so low? This is where multimeters really start giving you information that you might not otherwise have or even be aware of. Let me turn the heater off and I will explain. And the heater has been turned off, and you can see the voltage returns to its normal range. In this case, the reason the voltage dropped to 107 volts, which is considered to be below spec, you would not want to be lower than about 110 volts in North America. It is because the building in which I have this circuit that I'm measuring, and the heater plugged into, has an extremely long run of wire far out from the main source of power where the power company connects to the house. And there's a lot of voltage drop. The longer the wire, the more resistance it has, and therefore when you turn on a heavy appliance, you get what's called voltage drop. Due to the resistance in the wire, the voltage drops, and the current still flows, but it's at a lower voltage, and this is basically what we would call an inefficiency, because you're going to lose some of the power in the really long wire as heat. And that goes right into the next function that I'm going to show you on this meter, which is measuring resistance. Electrical resistance is simply an inhibition of current and or voltage flow in a wire. The longer the wire, the more resistance, and generally speaking, you want as low resistance as possible because an electrical voltage plus resistance generally equals heat, and the heat is simply lost electricity. You'll never get it back. It's just being wasted, and so that's why you generally want a good high quality thick cable with low resistance so that all the power goes through it and into your appliance instead of just warming up the power cord. And this applies to solar, applies to household electronics, anything at all. Same principles, works the same way. But a hidden feature of resistance is also continuity. So what if you want to know if a wire is broken? Again, a resistance check, continuity check are similar and pretty much the same thing if you want to look at it that way. In order to measure resistance, I'm going to come down here, and on the scale you will see that there is an ohm symbol. That's the symbol, Greek letter ohm or omega, and this means ohm. So ohms is simply a measure of resistance. And if you want to, you can look online and research how to calculate the resistance, voltage, and current on a circuit. I highly recommend learning that. Right here we have, again, a scale, and this is 200 ohms. That's a very low resistance. 1 or 2 ohms would be pretty low resistance, not very much, but it goes all the way up to 2,000, 20,000, 200,000, and even 2 million, or 2,000,000. I'm going to measure this really long power cord that I have that I was using for this example to see how much resistance it has. To do that, I only need to measure about 200 ohms or less, so I'm going to switch it to the most sensitive range, which is 200 ohms. And what will happen is the meter will, again, it should zero out. Now, different meters act different ways. Mine is a little bit odd. It shows a 1 and it shows a decimal place. It basically means, okay, I'm ready to take the measurement. Now, if you have a dead battery or there's something wrong with the meter, it may do something odd. I know this meter well, and I know it's ready to measure resistance. So what is the first step to taking a resistance measurement? Again, you want to make sure you're plugged into the right connections on the meter. We already talked about that. The first thing you do is you take your multimeter probes and you short them together. And the reason you do that is the probes themselves have a resistance. In this case, the meter says that the probes have about 0.4 or maybe 0.5 of an ohm of resistance in the probes and in the wires. So I have to take that account in my measurements. Now, sometimes you will see the reading vary or drop, but it's about 0.4 of an ohm. I'm calling it 0.4 of an ohm. And I need to know that because the cord is going to be a certain resistance, and I want to know what is the resistance of that cord. I do not want to include the resistance of my multimeter probes and wires because that would be inaccurate. Okay, here's that extension cord that you saw me use earlier. I've unplugged the other end, and this is a fairly thin and long cord, and I'm going to measure it using the ohms setting to see how much resistance it has. So first I'm going to take a probe and I'm just going to stick it in one side. And I'm just going to pick one side. It doesn't really matter. Now, as you know, there's two conductors in this type of cord. It's a two-prong cord, not a three-prong. And I can just touch it to one of these prongs and one of them should give me a reading. And let's go ahead and touch the probe to this side. And you can see I got the right one. And what I'm seeing here is about 0.5. So really, this cord has about 1/10 of an ohm of resistance. Now, what I shouldn't see, if I turn the cord around and touch the other side, I shouldn't get anything. And the reason is I'm not connected to that side. Now, if you want to test a bad extension cord using what's called a continuity check, you can actually see which side you're connected to and which side still has an intact functioning wire inside. And sometimes you have to wait a while for the reading to settle down. In this case, it takes a while. So effectively, this cord has a very low resistance, as I expect. I don't want to see like 3 ohms or 5 ohms on a cord like this. It's about 20 feet long. 5 ohms would be very, very high, and that cord, it's either a bad cord or it's going to get really hot in operation, and I wouldn't use it for anything important, or possibly even just throw it away. But this cord is fine, and 0.1 of an ohm or 1/10 of an ohm is very small and is nothing to be concerned about. Now, what if I stuck my meter probe in one side like this, and I got nothing? So every time I touch this, the meter says there's nothing there. It just doesn't do anything. A lot of times that means the cord itself is bad and you have a broken wire. Another trick you can use is simply attach the probe, get a good connection, and then start moving the cable around. Move the wire around and see if the reading changes. If it starts turning on and off, you know you have a frayed or broken wire inside the cord and you need to dispose of it. Now, to further demonstrate the value of a simple multimeter like this one, I'm going to show you how to do a continuity check and an ohms measurement all in the same run. In addition to that, I'm going to show you how to identify which cable is which. So in addition to a polarity check, a multimeter like this can help you identify which cable goes where. If it goes through a wall or underground, it can be very difficult to tell which one is which because they come out the other end and they all look the same. So here's some old solar panel cable I have. You can see the end has been cut off. This is a used cable. And what I'm going to do is check this cable to see which one is which. I don't know. It's a pile of cables, and this could be running underground, or it could be in a large installed system or anywhere. But I'm going to go ahead and touch my probes to one side of a wire that I see exposed, and you want to make sure it's not a live wire. In this case, I know it's not. It's just sitting on my work table here. Then I'm going to take the other end of it, and I'm going to put my probe in. Now I can touch this wire and see if that's the same wire. And you can see that it is. And this wire has, again, about 0.2 of an ohm to 1/10 of an ohm of measurement. So you can see that a multimeter has a lot of value. You can use the resistance or continuity check to see if a wire is broken or has high resistance or a bad connection. You can use it to identify which cable is which. And by switching it to voltage, you can even find which one is putting out power. If, for example, I had an array of solar panels and I had 20 or 30 wires coming through, I could disconnect the solar panels and use the ohms setting or the continuity check setting on the meter, if it has one, to determine which of these wires goes where and then mark them with a color tag at either end. And by process of elimination, I could identify every single wire, without actually seeing where they go underground or through the conduit or through the walls or wherever they're going. In this case, I know I just have a couple of solar panel cables on my workbench, but it's a great way to demonstrate how it works. So this cable here goes to this plug, and I know that because this meter told me that. I don't actually have to go and look at the entire wire foot by foot to see where it goes. Okay, next I'm going to talk about the probes themselves. Most basic multimeters come with a very cheap set of probes, and they're actually quite hazardous to use as the wire that's inside here can actually fall out or come loose. And generally speaking, they're not very good quality. So if you have a chance, it's a good idea to spend 10 or 12 bucks on a nice set of probes. They're just a little bit better quality than what the meter comes with. They generally cut corners on the probes, and it really shows. But I want to point out that at the end, generally speaking, you would have about, this much metal which is exposed. And that is one of the most hazardous things about using a multimeter. These metal probes here can actually get you electrocuted, and they can also cause a short circuit. They are conductive, and if you shove this piece of metal into the wrong place in a live circuit that's functioning, you can actually destroy it. And worse still, you wouldn't even know you did it. It may not necessarily make a spark, but you would have quietly destroyed that circuit, causing even more troubles. So probing a live circuit with probes like this is generally a no-no unless you're really an expert. Now, some probes come with a set of shrouds which will cover up this metal and only leave a little piece of metal at the end exposed. If you have those available, you should install them and use them in general and only take off the shrouds off of these metal probes when you need to do that. For example, when measuring an AC power outlet, you need the full length of the probe to get into the outlet to get a contact and measure the voltage. Otherwise, you should keep the probes covered up as much as possible to minimize the chance of a short circuit or an accident. Another common mistake is when measuring something that's close together and then accidentally contacting the probes together. Once again, it makes a short circuit. So very risky, and it's very easy to do that. It's so easy to slip with these probes and touch them, and it just takes a split second and you've made a short circuit. And you can see that these probes here have a little point at the end, and that's actually intended for penetrating wire, and it's also intended for getting a good connection. So if you wanted to, and I'm not saying I recommend this, you could actually take the multimeter probe and actually push it into the wire through the insulation and make a connection. I generally avoid doing this because I don't want to damage the insulation on my wire, but in some cases, in desperate situations, you may be forced to actually push through the insulation jacket of a wire, use the sharp point of the probe to get a voltage reading of a wire that is live and in circuit. This is mainly an FYI. I don't necessarily recommend doing it, and it's generally only for advanced users of multimeters. And keep in mind you are damaging the jacket or the insulation of the wire, and I would not want to really use an extension cord that had a hole poked in the insulation for any reason whatsoever. Another reason for the very pointy end of the probe is actually so that you can get a good connection. Sometimes there will be some oxidation or some corrosion on a measuring location, and by taking this probe and sort of scratching with the sharp end, you can actually get a good connection and take a voltage or a resistance measurement. At the end of the probe, or near the end of the probe, you can see where my fingers are. There's a finger guard, and generally speaking, you're not supposed to put your fingers past that line there. That's to protect your hands from slipping and making contact with the metal part of the probe. It's for safety, but I'll tell you, when I'm measuring a higher voltage or I'm worried in any way for my safety, I usually hold the probe back here, and I keep my fingers and hands as far away from what I'm measuring as I can. Just for instructive purposes, let's take some resistors, and these are supposed to be 15,000 ohms, and let's measure these to see what they actually are. So let's take the probes and put them right on the resistor here, and you can see that I don't really get anything on the meter, and that's because this is supposed to be a 15,000 ohm resistor. Let's bring it up to 20,000 ohms, and then let's try measuring the same resistor. And I get a reading of 14.78. It's jumping around a little bit, which is not a problem. Let's call it 14.8. So this is 14.8 thousand ohms. It isn't quite 15,000 ohms, but it's pretty close, and it's probably still useful. Even though the resistor is showing as less resistance than what it's supposed to be, it doesn't necessarily mean it's a problem. It's pretty close. It's not super perfect. This higher range right here obviously is useful for measuring higher resistances. Now, if you were to plug the meter into an extension cord and you had to come all the way up here to get a reading, it's time to throw that cord away, because an extension cord would never be 20,000 ohms or 10,000 ohms. You want it to be under 1 ohm, and a tenth of an ohm, half an ohm, would be probably the very most I'd be willing to accept. Another useful tip for using a digital multimeter is if the battery is not fresh and is low on charge, the meter may or may not tell you the battery's low, but I will tell you that it is a fact that when the battery gets low, these meters start to read inaccurately. The readings can change quite a bit depending on the status of the battery inside. In this case, I'm sure the battery is at least half charged, and I'm just showing some examples, so I'm not too worried about it. But if you're very concerned about the accuracy of the readings, make sure the meter has a fresh and charged battery installed first. Another obscure fact about this type of multimeter is it's very common that people will just take the dial and flip it over to what they want, and they don't pay a lot of attention. It's very possible that the meter can get stuck in between. So you can see right there, I've stopped it in between two different settings. And if you do that, the contacts inside this rotary dial here may not give you the results you expect, since this dial is actually part of the circuit inside the meter. So if you're ever getting strange readings, one of the things you can do is put it back on the setting, switch it over, and watch the dial. And what should happen is the meter should zero out. You can also try things like pushing on the dial. Sometimes if you push on the dial, you'll see the meter change its behavior, and that's usually a red flag. It could mean that the switch in here needs to be opened up and cleaned out with electronics contact cleaner, or perhaps it is faulty. The next function I'm going to cover is measuring current, or amperage. Amps is a measurement of how much electricity is flowing, or the quantity of electricity that is flowing through an electrical circuit. This information is fairly universal, so I'm going to use a simple battery, which is a 12-volt battery. You can pretend this is a solar panel, a battery, a DC power supply. It really doesn't matter. It all works the same. To measure current, there's two ways to do it. You have micro in milliamps here, and then you have 10 amps. Now, I generally pretty much never use these. The most common one I use is this one here, which is 10 amps. And I would not put 10 amps of current through this meter. But, 3 or 4 amps for a few minutes or seconds to measure your circuit and see what's going on should not be a problem. So in order to measure amps, you will use the common connection, which is right here. And instead of plugging it in here, which is for volts, ohms, and milliamps, so the very tiny fractions of an amp that are measured here, I'm actually going to plug it in here at 10 amps. And in order to make this easier, I've replaced my probes with alligator clips that are able to be plugged into my meter. So here are my alligator clip probes. I'm going to plug the negative into common, and then I'm going to plug the positive side into the amps. Now at this point, you don't want to try to take a voltage measurement, or you will short out the current right through the meter and destroy the meter. So I'm going to switch it over to 10 amps, let the meter zero out. Now I can go ahead and take a current measurement. For this example, let's use a fan. That is an electric fan or blower. And I'm just going to connect it to the battery here that I showed you earlier. When I connect the fan to the battery, it's going to turn on. And you can see that the fan is running. It's blowing air, and I can measure the voltage of the battery, which I did earlier. But what if I want to know how much current is flowing? In order to measure the current flowing in a circuit, you will no longer be placing the meter in parallel. When you place the meter over the terminals of a battery, you're effectively placing the meter in parallel with the output of the battery to measure its voltage. But in order to measure the current, or the quantity of current flowing through a circuit, you have to place this meter in series with the item that you're running, whether it's a fan, a light bulb, a solar panel, a charge controller. It doesn't really matter. The principle is always the same. So it's important to keep that in mind. Earlier, I connected a fan to my alligator clips, and the fan turned on. What I need to do is I need to run that power through these two connections here and then to the fan. Then I will be able to see how much current that this fan is burning. I've set up for the experiment. I have my cables going to my battery, which are right here. This is positive and negative. So this represents the output. Now I have two thin wires coming from the fan. That would represent my load. Now if I just want to run the load, I just connect it to the positive and negative on the battery, and it will turn on. But that doesn't show me how much current is flowing through the circuit. I know I can get the voltage by placing my meter across positive and negative of the power supply. In order to get the current, I'm going to attach the black alligator clip, which represents the negative of the battery, to the fan's negative. And that makes half of the connection. Now I have the battery, which is this alligator clip here, and the fan's positive connection. So what I'm going to do is, instead of connecting it straight to the fan, I'm going to insert the multimeter in circuit, and I'm going to close this connection here using the multimeter. This will cause the power to come out of the battery, into the meter, out of the meter, and into the fan, and it will give me the measurement. This is going to get a little confusing. I have two more alligator clips. They look slightly different. So before beginning the demonstration, let's be clear. These two alligator clips are attached to these two connections on the meter, common and 10 amps. So now this is a series connection. It's going right through the meter and out the other side. The meter is just measuring between these 2 points to see how much current is going to flow. So this meter has changed its operation. It's important to keep that in mind and understand it. Power is now going to flow through the meter through these two alligator clips. So I'm going to attach the positive alligator clip from my meter to the positive power source. Now that leaves me with a positive wire to the fan and this black alligator clip, which is actually going to be positive, because this is actually connected to the positive terminal of the battery, but going through the meter. So let's see what happens when I connect the positive fed meter to the positive of the fan. And now you can see that the fan has turned on, and it's drawing about 150 milliamps, or 0.15 of an amp. 150 milliamps is a very small amount of current, and I can leave this meter attached all day. As long as the battery in this meter doesn't run down, it's perfectly safe. There's not going to be any heat generated. That is a very, very small amount of power. But if you're measuring 5 or 6 amps, you would only want to do that for 5 or 6 seconds, and then you would want to stop, because a meter like this really isn't intended to be a high amperage meter, and it will get hot. Eventually it could melt or blow a fuse inside if it has one. So when I disconnect the meter, the fan stops and the reading stops. What if I want to know the voltage coming out of the power supply into the fan while the fan is operating? Obviously, when the fan turns on, the reading could change. And here's where a number one mistake is often made. You switch the dial straight to 20 volts, and you start taking the measurement. The problem is your meter is now in a short circuit. So I got to remember to always unplug this connection here and put it back where it belongs so I can take a voltage measurement. And if I don't, I can burn out the meter. So I went ahead and made that change. I've gone to 20 volts. Now I'm going to change the setup. Again, here is the battery output, or the solar panel, or the power supply, or whatever you want to pretend that it is. I'm going to connect that to the fan without the meter being in circuit. The fan has turned on. Now I've checked my meter. I'm verifying that it's currently back in common and voltage, ohms and milliamps, and not in the 10 amp range right here, or the 10 amp socket. I put the meter on 20 volts DC. Now I'm going to take the measurement of the battery or the power supply or whatever it is while it's in operation. So in order to do that, I simply take the power connection for the negative, and I'm going to attach my meter to that. Then I'm going to take the positive side right here, which is feeding power to the fan also, and I'm going to attach my meter to that side. And you can see that the loaded voltage present at the terminals of the fan is 13.22 volts, or 21 volts. It's jumping around a little bit, and that's perfectly normal, and it's nothing to be alarmed about. Now, this is all on a very small scale in a lab environment, but the principles are still the same. Let's disconnect the fan while leaving the multimeter attached and see if the voltage changes. And you can see that the voltage actually crept up just a little bit. It went from about 21 to 22 to 0.23. It was about 0.01 volt higher than it was with the fan running. And that's normal, and that's caused by the battery's internal resistance, or the load's power draw, which is going to pull the voltage down just a little bit. In order to fully get everything out of this multimeter that you can, it's highly recommended to study the relationship between resistance, voltage, and current. You can do that online in your free time, and it may take a while to understand, but once you understand it, it will change the way you look at electrical circuits of any kind, whether it's solar energy, household electronics, or anything similar. Even working on your car could be different. If you know how to use this meter and you understand resistance, current, and voltage, it will change everything. I hope this video helps someone. It does not cover all of the settings or functions on a typical multimeter. All multimeters are different and may have different scales, ranges, voltages, functions, and features. Thanks for watching, and I'll see you later.